When a magnet quietly hovers above a frosty block of material, it looks almost supernatural. Most people assume it's a clever trick or a hidden mechanism, but what you're seeing is completely real, a beautiful intersection of physics, materials science, and quantum behavior made visible in everyday life. The key to this phenomenon is the superconductor underneath the magnet. At room temperature, it behaves like an ordinary metal with nothing special to show, but when cooled down to extremely low temperatures, usually with liquid nitrogen, the atoms inside reorganize into a remarkable quantum state that changes everything. In normal materials, electric current faces resistance, electrons bump into atoms, impurities, and vibrations, converting energy into heat and wasting power. But once a material becomes superconducting, its electrical resistance drops all the way to zero. Electrons travel effortlessly, forming a kind of coordinated quantum flow that encounters no obstacles. However, zero resistance alone does not make magnets float. The real magic comes from how superconductors interact with magnetic fields. Their reaction to magnetic forces is not mild or partial, it is absolute. When a material transitions into a superconducting state, it completely changes the rules for magnetic behavior. Below its critical temperature, a superconductor expels magnetic fields from its interior in a process known as the Meissner effect. Instead of letting field lines pass through like typical metals, the superconductor forces them to bend around the outside. This creates a strong repulsive force that can push a magnet upward. If you place a magnet directly on a superconductor, the magnetic field is reshaped in a way that creates an invisible cushion. This cushion can counteract gravity, allowing the magnet to rise and remain suspended. The stronger and more uniform the magnetic field, the smoother and more stable the levitation becomes. But many real superconductors are what we call type 2 superconductors, and they behave a little differently. Instead of perfectly rejecting all magnetic fields, they allow controlled penetration through tiny channels known as flux vortices. These vortices act like microscopic tubes of magnetic energy threading through the material. Here is where levitation becomes truly stable. Those magnetic vortices get trapped in place by microscopic imperfections inside the material. This phenomenon, called flux pinning, locks the magnet into a fixed position. It prevents sliding, spinning, and sudden falls, allowing the magnet to hover as if frozen in mid-air. Because of flux pinning, you can tilt, rotate, or push the magnet, and it will maintain its relative position above the superconductor. It may shift smoothly along a track, move in a circle, or hang upside down, but it never breaks away. It behaves almost like it is magnetically glued to a path. This remarkable combination of the Meissner effect and flux pinning is powerful enough for advanced technologies. Maglev trains, for example, use superconducting magnets to eliminate friction entirely, enabling extremely high speeds with remarkable stability. Research is also exploring superconducting bearings, power systems, and even futuristic forms of transportation. The biggest limitation today is temperature. Most useful superconductors require cooling to extremely low levels, which adds cost and engineering complexity. Scientists are searching for high-temperature superconductors that could work closer to room temperature, a breakthrough that would transform energy transmission, transportation, and even computing. For now, the levitating magnet remains one of the most striking demonstrations of quantum physics in action. It reminds us that buried beneath ordinary materials are extraordinary behaviors waiting to be unlocked, and as research continues, the quiet floating magnet could become a preview of a future shaped by superconducting technology. That's it for today's video. If you enjoyed exploring with me, don't forget to subscribe to Science Lab, where we turn everyday things into scientific discoveries. See you next time.